Alrighty, my friends, hi again. So in this next video, what we're going to do is investigate the scientific method. Perhaps you've heard of this before, maybe in some of your, I don't know, maybe elementary, middle, high school science classes. Maybe this is your first time hearing about it, or maybe it's been a while. And so this is going to be a nice little, perhaps, reintroduction into what the scientific method is. So let us begin. Okay, so this is kind of an overall list of what the scientific method is. It's not necessarily linear, and this is something that you will actually read about in your book through Module 1.2. But this is kind of just an overall, like when you're maybe first starting out, this is kind of a nice little listeroo of some things that scientists go through. And like I said, it's not necessarily linear. In this particular case, it is numbered, but it's kind of a nice little stepping stone for this idea. So generally the first thing that we will do is to make an observation and generate questions about what we see. So, I observe outside right now that it's kind of cloudy, but it's also like little bit of blocks of sunshine. Why would there be a little bit of sun, and why are there some clouds out there? So I could investigate further. Okay, so what makes a cloud, for example, or why is today a little bit cloudier than it was yesterday? And then I would consult the literature and see what's already known about that topic or my question. So I'd go into Google and be like, okay, or Google Scholar, and be like, okay, what do we know about cloud making? Develop a hypothesis and then test or make a testable prediction based on your hypothesis. Remember, if we go back to the previous video, what is testable? What is scientifically testable? And then you will then design and carry out an experiment or observational study to test your hypothesis, analyze that data, and then draw your conclusions. Do your results support or refute your hypothesis? Refute simply means go against your hypothesis. Oddly enough, more often than not, our initial hypothesis is often incorrect, and that's an okay thing. That's straight up just meaning you're just learning, right? You're just learning about a thing, and I think that's really cool. Then the last thing that scientists do in particular is to communicate your results to the scientific community so that others can then review and likely criticize your work, and then add new knowledge to the field. So we're going to go through each of these steps a little bit further with just a kind of some silly little examples that I have here. So the first idea, to make an observation and then question things further. So maybe, you're wondering, what's the best time to drive to campus? Or what food does my animal prefer to eat? I don't know if anyone here has cats or dogs. Sometimes they're picky. Sometimes one of my cats loves to eat everything else except for chicken. Why would she hate chicken specifically? Is it something when she was a kitten before I had her? Like, what's the deal? But the question and the example that we're going to work through here in the next couple of slides is the heavy traffic on roadways. So the thing that we're going to do first, right? What's our number one thing other than making our observation and questioning is scientific literature. So we have to research whether or not this question has been asked before. So in our search bar, we would include your topic name plus the terms study, research, or meta-analysis. Google Scholar, like when you're looking for stuff, Google Scholar is an excellent resource for peer-reviewed articles. Any university or college institution's library also likely has a really nice database of scientific articles, which is a really nice resource to use. Simply using Google or Wikipedia or Bing, whatever search engine you use that doesn't look at peer-reviewed articles, generally in the scientific sense is not a good method. Then you want to read as much, once you've done your bit of your research, you want to read or you want to figure out as much as that particular subject to determine what has already been done, like 20 to 30 articles, okay? Not just like flipping through TikTok and finding a 2-minute video, or going on Instagram or whatever, going on Reddit, whatever social media thing you want to consider. You really like need to, it takes time to go through real articles. Second bullet point here, this process literally takes months when it's done correctly, okay? If you have a potential idea to go to grad school, or if you're going to pursue a senior thesis or a research project, literally one entire semester will be reading scientific articles, reading and writing and annotating. I may even have in here my old stacks of a lot of the things I had to read when I was in college. Yeah, I do. It's buried deep within my desk, but it is there. It's a stack literally like this big. It's pretty wild. So going back to our example of traffic, so a big thing here would be like, okay, have any studies been done concerning urban traffic, especially here in the Bay Area? So what's the impact of working from home versus going into the office? Are more lanes actually helpful? What about express lanes? What kind of impact could that even have on lower income folks? What's the impact of public transportation? I guarantee you the SFMTA has gone through these studies, or has attempted to pursue these studies. So from here, then we're going to generate our hypothesis. So a hypothesis is a testable theory on whatever question you want to answer. So from our research, perhaps we notice that one can find that there are many different things that can contribute to traffic. Weather being a big thing. I swear to goodness, people take their brains out of their skulls and leave it at home before they drive on the freeways here in the Bay Area. Sporting events. I personally live really close to Oracle Park and Chase Center. When there are sporting events going on, my goodness, it takes me so long to get home. Bad car accidents. This happened to me personally last Thanksgiving. That blocked 3 lanes on the Bay Bridge. It took me a very long time to get to the East Bay. How many people are coming into work? You know, things like that. There are multiple things that contribute to traffic here in the Bay Area. So my hypothesis, my main hypothesis here is that, you know, considering how many folks are coming to work, right? So less folks being forced to come into the office every day will then decrease the amount of traffic into and out of San Francisco. So we got to test this hypothesis, right? This was a way that it was tested in a fair way where it can be repeated and the conditions are constant. Of course, in my hypothetical question, it wasn't necessarily constant, or conditions weren't necessarily constant, but it was repeatable for several months, right? So our example early in the pandemic was a wonderful way to forcibly test this hypothesis, right? Many folks were then working from home, which meant there were way fewer cars on the road, thus way less traffic. Air quality also very highly improved, not just here in the Bay Area, but all over the world. Obviously now, you know, at this point, many companies are starting to require at least a few days being back in the office, and traffic has very, very much returned. It's also kind of interesting. You can kind of see the days that are perhaps required for tech companies, like Tuesdays and Thursdays or Mondays and Wednesdays. Like the traffic is greater on those days. And even like the foot traffic downtown as well has also very much improved. Of course, this is not a perfect experiment, all right, in this, you know, hypothetical situation. I'm not the one going out there and like measuring all this stuff. These are simply from observations, but of course, again, this is a hypothetical situation. I don't want to bore you with all of the details of the experiments that I've had to do in my time. So lastly, what we're going to do here, or second to last, I guess I should say, is analyze your data and then make conclusions on the data analysis. So what you're going to do is assume that you've very carefully constructed and tested your hypothesis where you're able to control for as many variables as possible. This can be really difficult sometimes in some trials and studies, like in medical trials and studies, for example, or nutritional trials, It can be really hard to really control for some of these ideas, but you do your best, right? And then you're going to analyze that data to see if your hypothesis was correct or incorrect. Again, like I said before, oftentimes our hypothesis tends to be incorrect. And then depending on your results, you may have to change your hypothesis or redesign your testing. This happens sometimes as well. Can't tell you how frustrating it is, but it's just the process of science. It's how it goes. And maybe you actually uncovered an even more interesting scientific question, and this can lead to new and exciting experiments and conclusions. Oftentimes in many talks that I've heard or poster sessions that I've gone to, they'll even have a little section of future work of things, new interesting things that have come to light. Then the last thing that we're going to do as a scientist after we've done all this amazing work is we're going to share our results, right? So you're going to detail your hypothesis and methods and result, and that is so crucial because in the peer review process, it has to be reproduced by other scientists, right? Or theoretically reproduced by other scientists. And also sometimes even a lack of a result can actually be an interesting result. So say if we, in our traffic study, if we're like, okay, well, what actually turns out that, there is no difference to people coming to work via vehicles rather than, working from home. There is no difference there in terms of traffic. That can be an interesting result too. And then really in most science worlds, there are three main ways to share your results. Number one way is to write a paper and submit it to a journal of your choice. This is a very arduous, long, and lengthy process when done correctly. It takes upwards of 2 to 3 years to complete. Can confirm it's not the most fun thing ever. Or two, you're going to go to a conference. And at the conference, you are either going to give a talk, an official talk, or you're going to present your information in a poster. So those are kind of the three main ways. Write a paper, give a talk, present a poster. Oftentimes also, when you do a talk or a poster, you're likely going to have submitted that information to a journal as well. But these are just nice, quick ways to get your information out there to a lot of people without kind of requiring them to read your paper. Last little thing I want to mention here, some things to keep in mind before sharing results, is that any scientific theory is falsifiable, frankly. There's no such thing as 100% proof. Results suggest conclusions, but do not prove them, right? That's kind of a very interesting use of words in science, is suggestions, not proofs. So we can prove phenomena exist, but it's much harder to prove the non-existence of something. Correlation is not causation. Extraordinarily important with everything here. Very important to distinguish the differences between the two. There was a study, which I'm happy to link somewhere, that showed a very strong correlation between the number of Nicolas Cage releases in a year and the number of drownings in swimming pools. Just because they correlate doesn't mean one caused the other, though that can be questionable. It's also, last thing here is to avoid windowing and cherry picking of ideas. And that one's really important. Oftentimes in mass media, things are cherry picked. Later on in the semester, we'll read a sort of cherry picked article and then rebuttals from that. But it's really quite important to not cherry pick your results and just proclaim those results as the final conclusion. Okay? Thank you all so much for watching. Appreciate it.